Hello, everyone, and welcome to another episode of the Threat Hunting 201 series. Today, we are covering technique for clustering. So, without any further ado, let's get right into it. So far in this series, we've done searching and filtering, stacking and sorting, and grouping. And each of those, you were the one defining what you were looking for, right? Show me the rare process. Show me everything around this user. Find this IOC. Clustering is different fundamentally. In clustering, you're not telling the system what to look for, you're giving it data and asking it to figure out which things are similar to each other. The algorithm decides the groups, not you. Let me just note this down. So, clustering is automatically grouping data points based on shared characteristics without pre labeling and without a predefined hypothesis. Now I know what the question is. Same question I got for grouping. How is this different from stacking? Right, fair. Let me answer that clearly. Stacking and sorting, you're asking what's the most common or what's the rarest. It's one field ranked by frequency. That's it. Grouping, you are anchored to one specific entity. You say, show me everything around this user, or show me everything around this IP. You define the pivot point. Clustering, you are not ranking, you are not anchoring to one entity. You are looking at the shape of the data across all entities simultaneously and asking which ones look like each other and which ones don't look like anything. Simple way to remember it: stacking ranks, grouping pivots, clustering profiles, right? And the key insight is this: stacking would miss a threat that happens frequently. If an attacker's tool is running 5,000 times a day, stacking puts it in the middle of your results. Clustering would still find it because its profile looks different, its parent process is wrong, its DNS structure is wrong, its combination of behaviors is wrong. That's why clustering exists as a separate technique. Now, when do you use it? The decision is, do you have a defined pattern you're deviating from? If yes, that's anomaly detection, which is next episode. If no, if you don't even know what the normal pattern looks like, that's clustering. You're letting the data tell you what groups exist. Also, and this is important, clustering is generally not your starting point. It's not what you run first. You use it when stacking and grouping haven't been enough, when you need to look at the data differently. One more thing, in Splunk, there's a dedicated cluster command, and MLTK gives you k-means, DBSCAN, all of that. In ESQL, we don't have those native commands, but we can replicate the same results using stats, eval, and case. And honestly, what I'll show you is actually more useful in a SOC context because the scores are explainable. You know exactly why something is in a cluster. Let's jump in. So in Splunk, the cookbook for process clustering uses XY series. It builds a literal pivot table. Parent process on one axis, child on the other, count in the cell. Rare cells are your leads. For DNS, Splunk MLTKs, DBSCAN clusters by string features directly. For host, fingerprinting means K3 across your metrics and you look at the outlier cluster. In ESKQL, we replicate all three with stats, eval, and case. No ML toolkit required, and the output is explainable. You can tell your IR team exactly why a host scored the way it did. Let's build them. 3 hunts, all exclusively clustering use cases, meaning stacking or grouping alone cannot do what these do. Hunt 4.1, process parent child matrix. Build a full relationship matrix across all parent child pairs. Surface the rare combinations without anchoring to any specific process. Hunt 4.2, DNS structural clustering. Find DGA domains by their string structure regardless of how frequently they're queried. Hunt 4.3, host behavioral fingerprinting. Multi-dimensional profiling of every host simultaneously. Surface the outlier cluster with an explainable score. Let's go. Alright, first demo. This one is about process relationships The hypothesis: unusual parent-child process combinations. In a healthy environment, Explorer.exe spawns Chrome, Word spawns WinWord related things. But if you see Word spawning PowerShell or CMD.exe spawning NLTS.exe, that's suspicious. Now, could stacking find this? Let's think. Stacking would tell you PowerShell ran 400 times. Okay, so what? It runs all the time. Stacking can't tell you that this particular PowerShell was launched by Word. For that, you'd have to do grouping, pivot on Word.exe, look at its children, but that only works if you already suspected Word. Clustering's approach is different. Build a matrix of all parent-child pairs across the whole environment. Count how often each combination happens and look at the ones with very low counts. You're not anchored to any specific parent. You're seeing the full picture. In Splunk, the cookbook does this with accessories. It builds a literal pivot table. Parent process on one axis, child on the other, count in the cell. Rare cells are your leads. In ESQL, we do it with stats and sort. Let me show you. I am in Kibana discover ESQL mode. Let me build this query from log, or I want all log data, where event.code equals 1. That's Seisman event ID 1 process creation. That's the event type that tells me a new process was spawned, and winlogged event data. Image is not null. Image is the child process field in Seisman, the full path of the process that was created, and winlog event data. Parent image is not null. Parent image is the parent, the process that spawned it. Now these are full Windows paths. C:\\Windows /system32 /cmd.exe. I don't want the full path. I want just the file name. So I'm using mv last of split on the backslash eval child process equals mv last of split of winlog.eventy data image on the backslash. This splits the path string into an array on every backslash and takes the last element. So C:\\Windows /system32 /cmd.exe becomes just cmd.exe. Same for the parent. Eval parent process equals mv last of split of winlogged event data. Parent image on the backslash. Now the clustering step, stats execution count equals count star, grouped by parent as process and child process together. This builds the matrix, every unique parent-child combination with its count. Now sort execution, count ascending, rarest combinations come first, limit 50. Let me run that, right? So I'm grouping by both parent and child together. That's the key. Not just how often does cmd.exe run, and that would be stacking, but how often does this specific parent spawn this specific child? That's the relationship pair. And sorting ascending means the rarest pairs are at the top. These are your small clusters, parent-child pairs that have happened only once or twice across the entire data set. That's unusual. That's potentially suspicious. Now let me add a filter. I only want pairs that happen 5 or fewer times. So where execution count less than or equal to 5. Run again. Look at these results. These are your leads. Every row here is a parent-child relationship that is rare in your environment. For each one of these, you now pivot. You go back to grouping. Filter on that specific parent process and that specific child process. Look at what else happened around that process at that time on that machine. What network connections were made, what files were written. The clustering step gave you the lead. The grouping step gives you the story. Second demo, DNS clustering. And this one I really want you to understand because it shows something stacking fundamentally cannot do. The problem: domain generation algorithms. DGA malware generates domain names algorithmically. Names like A4B8 seeds who D199F3.malware.io, xk9p.kbz.evil.com, long random looking strings. The malware queries these domains looking for its C2 to be alive. Now, Can stacking catch DGA? Sort of. If the domain is queried rarely, it shows up as rare. But here's the problem. If the malware is beaconing frequently, that domain is queried a lot, stacking puts it in the middle, not rare at all. Clustering on string structure is different. A legitimate domain like mail.google.com is short, depth of 2. A DGA domain like a4bhc2d19.malware.io is long and has a lot of numbers and characters in it. We cluster by structure, not by frequency. Frequency is irrelevant. A legitimate domain that's queried 5,000 times a day is still short. A DGA domain queried 5,000 times a day is still long. Structure clustering finds it either way. Let me build this step by step. From logs. Again, all log data where dns.question.name is not null. I only want events that have a DNS query name, and dns.question.name does not equal empty string. Filter out any empty values. Right, now I'll compute some structural properties of each domain. These are the features I'm clustering on. Eval domain length equals length of dns.question.name. Simple. How long is the full domain string? Eval subdomain depth equals length of dns.question.name minus length of replace of dns.question.name replacing with empty string. Let me explain that. Replace takes the domain string, finds every dot and removes it. The length of the string with dots minus the length without dots tells me how many dots there were. How many dots equals how many subdomain levels. Mail.google.com has 2 dots, depth 2. a4b8c2d19f3 subdomain.malware.io has 3 dots, depth 3. Now, important note. In ASQL, the replace function uses regex pattern matching, and in regex a plain dot means match any character. So if I wrote just a dot in the replace pattern, it would match everything and strip all characters, not just dots. I have to write it as square bracket dot square bracket. That's regex syntax for literal dot character only. This is a common gotcha. Now group and aggregate. Stats query count equals count star. How many times was this domain queried? AVG length equals AVG of domain length. AVG depth equals AVG of subdomain depth. Grouped by DNS question.name. Let me run that to see the shape of the data first. Good. Now I can see every domain that appeared in DNS traffic with its average string length and average subdomain depth. Now let's filter for the DGA structural profile. I want long domains where AVG length greater than 30. Sort AVG length descending, limit 20. Run, right? Any domains appearing here, long string, high character count, these are your DGA structural suspects. The string structure placed them in this cluster, not how frequently they were queried, not how rarely. The shape of the domain name itself, a legitimate domain that's long, could happen. Some enterprise software has long domain names, but extremely rare. And when you see one, you investigate, pull up that domain, find which machines queried it, look at what else those machines did around the same time. That's the cluster. Now grouping takes over. Filter on that specific domain, pivot on the source machine, look at everything that machine did in that time frame. Third demo, this is the flagship one. Multidimensional host behavioral fingerprinting. So in Splunk MLTK, you do k means k equals 3 with your feature columns. The algorithm takes multiple dimensions, multiple metrics per host, and automatically groups all your hosts into 3 clusters. Then you look at the outlier cluster, the hosts in the smallest, most unusual cluster. In SQL, we do this manually, and as I said before, the manual version is actually better for SOC work because you can explain it. The idea: build a behavioral fingerprint per host using multiple dimensions simultaneously. Event type variety. How many different kinds of events does this host generate? Process diversity. How many unique processes run on it? Network spread. How many unique destination IPs does it talk to? User diversity. How many unique users are logging into it? Then score each host on all dimensions combined. The hosts with the highest combined scores are your outlier cluster. Can stacking do this? No. Stacking would look at one field and rank it. Which host has the most events? That's it. It can't combine 5 fields into a profile. Can grouping do this? No. You'd need to already know which host to pivot on. Clustering tells you which host to pivot on in the first place. This is exactly the scenario where you need a technique that profiles all entities simultaneously without a predefined hypothesis. From logs all data where host.name is not null, I only want events that have a host name. Now the fingerprinting step, stats, and I'm computing 5 dimensions per host simultaneously. Total events equals count star, raw volume, event type variety equals count distinct of event category. How many unique event categories does this host generate? An endpoint that only generates process events has variety 1. An endpoint generating process, network, file, authentication, and registry events has variety 5. That variety itself is a signal. Process diversity equals count distinct of winlog.event data image. How many unique processes have run on this host? A normal workstation might have 50 unique processes. A compromised one running lateral movement tooling, credential dumping, and multiple C2 beacons might have 200. Desktop spread equals count distinct of winlog event data destination IP. How many unique destination IPs has this host connected to? A workstation talking to 5 IPs is normal. One talking to 200 is suspicious. Unique users equals count distinct of user.name. And how many unique users have logged into this machine? A personal workstation should have 1 or 2. A machine with 15 unique users in a month is a red flag. That's lateral movement territory, all grouped by host.name. Run that, right? So now I have a fingerprint for every host in my environment, 5 dimensions. Every host has a row. Now I score it. Eval behavioral score equals event type variety times 4 plus process diversity times 2 plus dest ipad spread times 3 plus unique users times 5. The weights are tunable. I'm giving the highest weight to unique users, 5, because multiple unique users on one machine is a very strong lateral movement signal. Network spread gets 3 because talking to many unique IPs is suspicious but has more legitimate explanations. Process diversity gets 2 because some machines legitimately run a lot of processes. Event type variety gets 4 because a host generating every type of event is unusual. You tune these weights based on your environment. That's the power of the manual approach. Now band them into clusters. Eval cluster sort band equals case behavioral score greater than or equal to 100. That's outlier behavioral score greater than or equal to 50. That's elevated. Everything else is baseline. Sort behavioral score descending. Run. These are your hosts sorted by their combined behavioral score. The ones at the top, the outlier band, are the equivalent of the small cluster k-means would return. The hosts whose combination of behaviors is unlike everything else in the environment. Pick the top ones, go back to grouping, build the full entity chain, what processes ran, what network connections were made, what users logged in, what files were written. And the beautiful thing, when you escalate this to your incident response team, you can say exactly why. This host scored 461. It had 6 unique event categories, 114 unique processes, 58 unique destination IPs, and 7 unique users. The environment averages 2 event categories. and 10 processes. That's actionable, that's explainable, that's an escalation an analyst can act on. And this is the point I want to drive home. The evil based approach versus the black box ML approach. K means in Splunk MLTK would do this automatically and give you 3 opaque cluster IDs: cluster 0, cluster 1, cluster 2. Your host is in cluster 2. Why? Because the algorithm said so. You don't get a reason, you get an ID. Try escalating that to an IR team. Try writing a ticket that says, host is in cluster 2, please investigate. That goes nowhere. The analyst doesn't know what to look for. The manager doesn't know how to prioritize it. The CSO can't explain it in a board meeting. Our approach says THOR-HQ Windows scored 461, outlier band. It had 6 unique event categories, 114 unique processes, 58 destination IPs, and 7 unique users. The environment average is 2 event categories and 10 processes. That's an escalation you can actually hand off. The analyst receiving that ticket knows exactly what to focus on. The 7 unique users, the 58 destination IPs, the weights are visible. The score is reproducible. You can tune it as your environment evolves. You can explain it to your CISO in plain English. When you escalate this to an analyst, you can say exactly why this host is in the outlier band. That matters in a real SOC. Alright, so that's clustering. 3 demos. 1, process parent-child matrix. Rare combination pairs, the thing stacking can't see because it only ranks single fields. Stacking tells you PowerShell ran 400 times. Clustering tells you this specific PowerShell was launched by Word, and that combination has happened exactly once in your entire dataset. 2, DNS Structural Clustering, DGA detection by domain string characteristics. The thing stacking can't see because the domain might be queried frequently. Stacking misses it. Structure clustering finds it regardless. 3, host behavioral fingerprinting, multi-dimensional profiling. The thing stacking and grouping can't do because they only look at one dimension at a time. Clustering combines 5 dimensions into a single explainable score and surfaces your outlier cluster. The full ESQL queries will be on my GitHub. Link in the description. Next episode is anomaly detection and forecasting. That's where you have a defined baseline and you're measuring deviation from it. Different from clustering. In anomaly detection, you know what normal looks like. You're asking, how far from normal is this? Clustering doesn't assume a normal. That distinction matters. And episode 5 will build directly on what we did here. If you found this useful, share it, tag me on LinkedIn, send it to someone in your team. It genuinely keeps me going. Thank you for watching. See you in the next one.